questions 11 through 20 on the 2008 grade 12 AMC 12A. 3 cubes are each formed from the pattern shown. They are then stacked on a table, one on top of another, so that the 13 visible numbers have the greatest possible sum. What is that sum? So first and foremost, let's figure out the sum of 3 cubes that all have those numbers. So it'll be 1 plus 2 plus 32 plus 4 plus 8 plus 16, and of course all times 3. And that equals 3 times 63, which is 189. And that is if all the faces were visible. But when you stack them on top of another, they're saying that only 13 faces are visible. So that means you've got one cube like this, you got another cube right below, and then you got another cube right below. Correct? And that means that on the ground is the face that you can't see. So on the ground you got one face that you can't see. Here you got 2 faces that you can't see, right? The face that's the top face of that cube and the bottom face of this cube. And then here you got another 2 faces that you can't see, the top face of that cube and the bottom face of that cube. So from this 189, I've got to subtract 5 numbers, right? Because there's 18 in total faces, but 5 of them are not visible. And that means there's 13 left. So I've got to subtract 5 numbers from there. And I have to do so that the end result is the greatest possible. So I've got to subtract small numbers. Well, the first thing I notice is that in this first cube, the top and bottom have to be on the same cube. So how do I make the top and bottom the smallest sum? Well, looking at this, 32 and 1, that's 33. 2 and 16, that's 18. 4 and 12, that's 12. So 4 and 12 would give me my smallest. So 4 will be here, and the 8 would go here. 4 and 8. And then very similarly, the next cube, the exact same thing. 4 on the bottom face and 8 on the top face. Now I just have to worry about the bottom face of the top cube. I want to make it the smallest possible. And the smallest possible number is 1. So the bottom face on the top cube will be 1. So I'm subtracting a 4, an 8, a 4, an 8, and then a 1. So I'm basically doing 189 minus 12. 12 is 24, 25. So 189 minus 25, and that is 164. And that's the greatest possible sum. So 11, the answer is C. A function f has domain 0, 2 and range 0, 1. The notation AB denotes that x is between a and b. What are the domain and range, respectively, of the function g, defined by g at x is equal to 1 minus f at x plus 1? So this is translations of functions. And this essentially means that you first start off with f at x, and then you are going to eventually translate f at x going somewhere, either left, right, up, down, inverse, reflection, things like that. And then we have to figure out how does the x values change, which is the domain, and how do the y values change, which is the range. All right. So first thing is, what is g at x? It is 1 minus f at x plus 1. Now I'm going to change the order a little bit. I'm going to say minus f at x plus 1 plus 1. Okay, a little bit easier to explain that way. Okay, first let's just concentrate on the domain right here. X, I am basically translating this by pushing it 1 unit to the left. All right, so that means that before we had x, y, now the x is going 1 unit to the left, so it's becoming x minus 1. So I know that may cause a little bit of confusion for some students, so I'll try to explain it a little bit. This original x right here. Let's say I call that x1. And now I've gone x plus 1, right? So that means that x1 is the equivalent of x plus 1. This is the equivalent of this. And that means that if you isolate for just x, it's x1 minus 1. So this was x1 originally, and when I translated it, it became x1 minus 1. Okay, so I hope that makes sense. Now we have to think about what happens to y. Okay, so what happens to y is, first and foremost, we add a negative in front of it. Remember, y is the same as f at x, right? So first, in front of this f at x, this right here, we added a negative, so it becomes negative y. And then once you do that, you're adding a 1, so plus 1. So there you go. That is something that some of you could do that extremely quickly, within like 5 seconds, but I wanted to talk you through it. Okay, well, now I have to figure out what happens to my domain and range. So for 0, 2, what happens to the 0? Well, it's going to be x minus 1. So 0 becomes negative 1. And then 2 is also part of the domain, which is the x values. So again, x minus 1. So the 2, I subtract 1, and that becomes 1. So this is my new domain. For the range, I'm going to be doing this, minus y, and then add 1. For 0, minus 0 plus 1, so it just becomes 1. And then for 1, minus that, so that's negative 1 plus 1 would be 0. And this is probably better written in this format. So there you go. Which answer choices match that? Negative 1, 1, 0, 1 for number 12 is B. Points A and B lie on a circle centered at O, and angle AOB is 60 degrees. The second circle is internally tangent to the first and tangent to both OA and OB. What is the ratio of the area of the smaller circle to that of the larger circle? Let's first draw a diagram here, and let's see what kind of scenario we have. So we've got O right in the middle, and let's draw our point A, and then B is going to be 60 degrees, right? So approximately like that. So let's label this now. This is A, this is B, and this is O. And this whole thing in here is 60 degrees. And that's what they tell you right there. Okay, now what they're saying is that there's another circle inside this region. So something like this. And let's draw in some tangent lines. So if this is the center of this smaller circle, we can draw a line from there to that tangent point, and similarly from there to there, and also from here, the center to the other tangent point like that. And these are of course all 90 degrees because those are tangent points. Okay, so at this point, let's connect O to that line, so like this, and here we go. So this is our diagram. Now the radius of the small circle I'll just call small r, so these are all small r's, and the radius of the big circle from there to there I'll call large R, and therefore this region right here, right there, is large R minus R, correct? And then now, the heart of this question is we have to concentrate on this triangle right here, that one. And we are told initially that that's 60 degrees. Now, when I cut this line down the middle, it cuts that angle in half, so this becomes 30 right here. And since this is a right angle, this is 60 degrees, right? Because the sum of the angles of a triangle add up to 180. So this is a 30, 60, 90 triangle. And the ratio of the sides, as always, are 1, 2, and root 3. The ratio of the sides of a 30, 60, 90 triangle. So we can use that ratio to compare R minus R to R. So R minus R over R is equal to 2 over 1. That's it. So cross multiplying, you get r minus r is equal to 2r. And then isolating, we get big R is equal to 3 small r. There you go. Now they want the ratio of the area of the small circle to the area of the big circle. And then we just substitute in what we just found. So the value for large R is 3 small r. So this becomes pi small r squared, pi 9r squared. And therefore this is 1 over 9. So number 13, the answer is B. What is the area of the region defined by the inequality 3x minus 18 absolute value plus 2y plus 7 absolute value is less than or equal to 3? All right, so this is a painful question that takes a long time. I'm very surprised that it's this early in the contest, but I'll try to make it as painless as possible. So here we go. This is really 4 separate lines, and as follows. The first scenario is when x is greater than or equal to 6 and y is greater than or equal to minus 7 over 2. When that is the case, we have to write this in the following form. We just drop the absolute values and it just becomes this. Now I'm going to set it equal. Why? Because I want to create boundaries. And those boundaries will allow me to figure out the area of this region. Right? So this first one is going to be of this nature. And solving for this, we get y is equal to minus 3 over 2x plus 7. So this is my first boundary, equation number 1. The next scenario is when x is less than 6 and when y is still the same, greater than or equal to minus 7 over 2. In this case, what you do is it will be negative 3x minus 18, like that. And then the other side, you just drop the absolute value, like this. Okay? So no tricks here, all right? Just doing exactly the way you would normally do it. And this one, if you isolate for y, you get 3 over 2x minus 11. And this is equation number 2. The next scenario is when x is greater than or equal to 6, but y this time is less than minus 7 over 2. In this case, the first guy stays the same, but the second one has to be multiplied by negative 1. 2y plus 7. And this equals 3. And isolating for y, this one will give you y is equal to 3 over 2x minus 14. And this is equation number 3. And finally, the last one is when x is less than 6 and y is also less than minus 7 over 2. And when they're both less than that, they become negatives for both of them, like this. You got to multiply negative 1 by both of them. And this one, when you isolate for y, it gives you minus 3 over 2 plus 4. So there we go. We've got our 4 equations for 4 scenarios. And those are the boundaries of our region. Now I have to plot these. Now, if I plot them, I can just put them very loosely on a XY plane like this. Now, I'm not going to be super accurate here. These 2 lines, or 4 lines I should say, they're 2 sets of parallel lines. So as you can notice, this slope and this slope are the same. And this slope and this slope are the same. So they're 2 parallel lines. So something like this. One line is going this way, another line is parallel going this way. And then, let's see here. So approximately something like this. And then we got 2 more lines that are going the other way in terms of the other direction. So one line like this and another line something like this. Okay, so you get the point. Now, our region is the region that is right there. The boundaries basically is what we calculated. So what they're asking us is to find the area of that region. Well, how do we do that? Well, we have to now, unfortunately, figure out these points, these intersection points. Okay, so let's label this. This was equation 1, this was equation 4, right? Those two were parallel. And then this guy here down here was equation 2, and this was equation 3, right? Because those are parallel since they have the same slope. All right, so you guys know how to figure out the intersection of two lines, right? You just set them equal to each other. For example, let's say I want to find this intersection point right there. That is the intersection of equation 3 and equation 4. So here's equation 3, here's equation 4. So I set them equal to each other. So it would be 3 over 2x minus 14 is equal to minus 3 over 2x plus 4. So this becomes, let's see, adding both sides, we get 3x is equal to 18, and therefore x is equal to 6. And then plug x equal to 6 back into either of these equations to get the y value. And when you do, you get, let's see here, 3 times 3 minus 14, so you get y is equal to minus 5. So that means that this point is 6 minus 5. Okay? In a very similar way, this point right here, I can figure out, and when I do, it's 7 minus 7 over 2. And this point right here is 6 negative 2. And this intersection point, that vertice of that shape, is 5 minus 7 over 2. So when I look at these points, that essentially proves to me that this is actually a rhombus type of shape. And the area of a rhombus is calculated as follows. You take the first diagonal, you multiply it by the second diagonal, and you divide by 2. So the first diagonal, for example, is from there to there. Second diagonal is from there to there. And the good news, the only good news about this question, is that to calculate the diagonals is fairly straightforward. The first diagonal from there to there is just going from minus 2 down to minus 5, right? So that is just 3. You're translating 3 units. So the first diagonal is 3. And the second diagonal from there to there, if you notice, you're going from 5 to 7 on the x-axis, and that's translation of 2 units. So the second diagonal is 2. So there you go. Finally, we get the area, which is equal to 3. So number 14, the answer is A. Let k equal 2008 to the power of 2 plus 2 to the power of 2008. What is the units digit of k squared plus 2 to the k? So k is equal to 2008 to the power of 2 plus 2 to the power of 2008. All right? Well, this first number is not too big. We can do that. 4032064. But this number is way too big to calculate, even on a calculator. But the good news is I can figure out what is the units digit of just this. How? Well, let's talk about this. Let's first of all write down the first few powers of 2. And when I do, you will see a pattern very quickly. So 2 to the power of 1 is 2. We got 4, 8, 16, 64, 128. 32, 64, 128, and 256. Now let's talk about the units digit here. Units digit. What is the units digit for each of these? It's 2, 4, 8, 6, and then 2, 4, 8, 6. So you can see clearly it's a repeating pattern. And that's always going to be the case. 2, 4, 6, 8. 2, 4, 8, 6. So how do I figure out the units digit of 2 to the power of 2008? What I like to do is just look at 2 to the power of 4, 2 to the power of 8. Anytime the exponent is a multiple of 4, as in 4 and 8, the units digit is 6. Okay? And similarly, you can do that for any number, backwards and forwards, from 4 being a multiple of 4. So 2008, the first thing you want to figure out, is it a multiple of 4? Yes or no? And the answer is yes, it is. So its units digit is 6. Okay, so the units digit of k, you're adding 4 to a 6, and that gives you 10. So the units digit of k is 0. All right, so that's very important. So let's first look at this one very quickly. K squared plus 2 to the power of k. Well, the units digit of k is 0, so the units digit of 0 squared will be 0. Now, I've got to figure out 2 to the power of k, what is the units digit? But that is a little bit trickier, right? Because I've got to figure out where in this pattern does k lie. Is it a multiple of 4? Is it not? Is it a multiple of 4 minus 1? You know what I mean? Like 3 is a multiple of 4 minus 1. Is it a multiple of 4 minus 2, which would be 2? So that's the next part of this question. And that can be done fairly quickly also. Go back to what is k. It's 2 to the power of 2008 to the power of 2 plus 2 to the power of 2008. Well, 2008 is 251 times 8, which is 2 to the power of 3, right? All to the power of 2. And then this one here, we combine and you get 2 to the power of 6 times 2 to the 251 to the power of 2 plus 2 to the power of 2008. And then you can factor out 2 to the power of 6 from this whole thing, and that just leaves you with this 251 squared plus 2 to the power of 2002. Now the whole purpose of doing this is to understand that 2 to the power of 6 is a multiple of 4. It's 4 times 16. And this whole thing inside, which is of really no importance to us, we just wanted to figure out what was k. Is k a multiple of 4? And the answer is yes, it is. So because k is a multiple of 4, its units digit will be 6. So 2 to the power of k. K is a multiple of 4, its units digit is 6. So there you go, 0 plus 6 is 6, and that is the units digit of this expression. So number 15, the answer is D. The numbers log of A3, B7, log A5, B12, and log A8, B15 are the first 3 terms of an arithmetic sequence, and the 12th term is log B to the n. What is n? So an arithmetic sequence basically means you've got A plus D, A plus 2D, and so on, right? That's an arithmetic sequence. The first term, the second term, third term, and so on. The 12th term will be A plus 11D, following the same pattern. And they tell us that the 12th term is log of B to the power of n. And they don't put a base, so I'm assuming that's base 10. If there's no base written, then it's base 10. And then A, they tell you, the first term is log of A3, B7. The second term is log of A5, B12. And the third term is log of A8, B15. All right, so how do we proceed here? Well, the fact that they're an arithmetic sequence helps us, because in an arithmetic sequence, if you take the second term, which in our case, or any case, is A plus D, subtract from it the first term, it will be the same as if you took the third term and subtracted from it the second term. Because watch, you get D on this side, and you get D on that side. So we're going to do the same thing with these 3 guys. Exact same. Take the second term, A5, B12, and subtract from it the first term, A3, B7, like that. And that's equal to the third term, subtract from it the second term, A5, B12, like this. Okay, and this is going to help us. So in log rules, if you have anything like this, it just becomes one over the other. So A5, B12 over A3, B7. And similarly, the same kind of story over here. A5, B12. All right, simplifying, well, we can drop the logs actually. Since the log of this is equal to the log of this, those two have to be the same. And if you drop the logs, you just get this is equal to this. But we can simplify a little bit. A squared B5, and this side is A3 B3. Divide both sides by a squared, and you're going to get just an a. Divide both sides by b to the power of 3, and this is going to be just b squared. So there we go. That's a very important relationship that we just got. Okay? That a is equal to b squared. So now we have to figure out the 11th term. Okay. How do we figure out the 11th term? Well, the 11th term, or sorry, the 12th term is a plus 11d. And that's why I'm thinking 11, because it's a plus 11d. All right, so a plus 11d is what I have to figure out. And they've told me that is equal to log of b to the power of n. All right, well, no problem. A I can figure out, and b I can figure out. A from up here is the log of A3, B7, and then 11d. D is basically the second term minus the first term, right? Exactly what we did here. That gives me d. And the good news is we've already simplified that right here. So it's 11, the log of this simplified is a squared b5. Correct? Hope you're following. I'm not doing anything tricky here. Okay. And then this is equal to the log of b to the n. All right. So this is what we have to solve, keeping in mind that a is equal to b squared. So since a is equal to b squared, I'm going to substitute that in everywhere. Everywhere there's an a, put in b squared. So the log of a, so this becomes b to the power of 6, b to the power of 7, and then plus 11 log of a squared, so that's b to the power of 4, b to the power of 5, and nothing has changed on this side. All right, so this becomes the log of b to the power of 13 plus 11 times the log of b to the power of 9, and then log of b to the power of 13. This 11 we can put here, b to the power of 9, 11 like that. That's a log rule. And then this becomes the log of b to the power of 99, log of b to the power of 13. And you multiply them now. Log rules, b to the power of 13 times b to the power of 99. And that is log of b to the power of n. And then finally, this becomes b to the power of 112 is the log of b to the power of n. So there you go. So n is obviously 112. And let's see, what is that going to give us? The correct answer, yay, one of the answer choices. So 16, the answer is D. Let a1, a2, and so on be a sequence of integers determined by the rule an is equal to an minus 1 over 2 if an minus 1 is even, and an is equal to 3 an minus 1 plus 1 if an minus 1 is odd. How many positive integers, a1 less than 2008? Is it true that a1 is less than each of a2, a3, a4? We have to make a table and work through this and see what kind of a pattern we get. So it's a little bit of a time drain. That's what I call these kinds of questions. Unfortunately, you have no time on a math contest, but let's see what we can do. A to the n is equal to a n minus 1 over 2 if a n minus 1 is even. And a n is equal to 3 a n minus 1 plus 1, or I should say, if a minus 1 is odd. So that is the only rules we are given. And they're saying that A1 is less than or equal to 2008, and they're all positive integers. So we'll start with the smallest possible positive integer, which is 1 for A1. And then we will see what are the values for A2, A3, and A4. And if A1 is indeed less than each of those, we'll put a little check mark beside it. And then we'll get some sort of a pattern, because obviously we're not going to do it for every one up until 2008. So if A is 1, using these formulas, let's see what we get. These formulas right here. A is 1, so for A2, since A1 is odd, I get 4. Since that's even, I use this formula, and that gives me 2. And then since this is even, this gives me 1. Is this statement true? No, it's not. All right, so let's keep going here. If it's 2, A2 is 1. Well, immediately I can stop because this statement is not going to be true. A1 is already greater than A2, right? So let's keep going. 3. This will be 10, and this will be 5, and this will be 16. Great. This is valid in terms of our conditions. So keep going. 4, that gives me 2, gives me 1, and this is therefore not going to work. I immediately notice that when A1 is even, it's not going to work because immediately you have it to get A2. So the first thing is that A must be odd, A1. So that's my first condition. And actually, a better way of saying it, in my opinion, is that A1 can't be even. I think that's a better way because 1 was odd and 1 didn't work, right? So, you see what I mean? All right, so let's keep going here. Let's only concentrate on the fact that it cannot be even. So let's just only do odd numbers. So I got 5. For 5, I get 16, 8, and then 4. So that doesn't work. For 7, I get 22, 11, and 34. Okay, that works. For 9, I get 28, 14, and 7. That doesn't work. For 11, I get 34, 17, and 52. That works. Yeah. And remember, just in case you're wondering where I'm getting these numbers from, just employing these rules given in the question. For 13, I got 40, 20, and 10. Does that work? No, it doesn't. For 15, I get 46, 23, and 70. For 17, I get 52, 26, and 13, and that does not work. For 19, I get 58, 29, and 88, and that does work. So as you can see, I mean, I think by now you get the pattern here. I'll just do a couple more just to sort of ensure that you understand that there is a pattern, as you can probably already see. Let's circle the ones that it worked for. 3, 7, 11, 15, 19, 23. So you can clearly see that every time you go up by 4, it works. So when A1 is equal to 3, 7, 11, 15, 19, 23, ... Every time you go up by 4, it's going to work. And we're going up, the highest we can go is 2007. And if you keep doing that, you get up to 2007. Actually, the highest you can go is 2008 because it's equal to, less than or equal to. So these are the only A1 values for which A1 will be less than each of A2, A3, and A4. So how many of those do we have? Well, let's see here, it will be 2007 plus 1 divided by 4. That's how you figure this out, and that is 502. So number 17, the answer is D, Triangle ABC with side lengths 5, 6, and 7 has one vertex on the positive x-axis, one on the positive y-axis, and one on the positive z-axis. Let O be the origin. What is the volume of the tetrahedron OABC? Let's draw our coordinate plane. We got y, x, and our z-axis out here. Okay. And then let's draw in our coordinates. That's x, that's y, and this is z. And they're saying that one vertex is on the x-axis, one is on the z-axis, and one is on the y-axis. Okay, so that is how we label this, and this can be labeled in any way. I'm not really sure which one is A, which one is B, but it doesn't really matter. I think A, B, and C like that. And then in the middle, this is O. So when you connect the dots here, you connect the lines, you form obviously initially a triangle with ABC, but then if you include O into the picture, it becomes a tetrahedron. All right? And they want us to figure out the volume of the tetrahedron. Okay. Well, let's see here. So the volume of the tetrahedron is going to be 1/3 times the base times the height. So that's the first thing that we have to establish. The base, several ways of doing this, but I'm just going to do it the way that sort of looks at me, where, let's see here, there's lots of ways of doing this. Let me not commit to anything right yet. Let me figure out the variables first, but this is accurate. Okay, so the first thing we want to do is obviously we need some distances. We need this distance from here to here. I'll call that x. We need this distance from here to here, and appropriately I'll call that y, and we need this distance from O to C, and I'll call that z. So how do I get those? Well, they have given me some important clues. They've given me the lengths of that triangle ABC. They don't really indicate where, so I'll just write it in. I'll make that 5, I'll make this 6, and I'll make this 7. All right? So that diagram is going to help me solve for x, y, z. Now let's return to this. The area of the base, if I call, like I said, it doesn't really matter. If I call this the base, it's 1/2 x times y. And if I call this the height, that's perfectly fine. That will be z. So this really just becomes 1/6 x, y, z. Okay? So if I can figure out the value of x, y, and z, I'm done. I can figure out the volume. Okay, so we're going to use this and a whole bunch of Pythagorean relationships. All right, where do we begin here? First, let's just talk about this one. That's a Pythagorean relationship. So that's z squared plus y squared is equal to 7 squared. And then this one here, again, Pythagoras, we get x squared plus z squared is equal to 6 squared. And then finally, this guy is x squared plus y squared is equal to 5 squared. All right. Okay, so we got 3 equations, 3 variables, and we can solve. So I'll just do, in any way is perfectly fine. I'll just do it like this. Isolate for z squared, and then isolate for z squared over here. 36 minus x squared. And then therefore, this is equal to this. So we got 49 minus y squared is equal to 36 minus x squared. And I think that should be good enough. Yeah, all I have to do is just substitute for one variable now, and that's where this one comes in. I can just isolate for x squared here, 25 minus y squared, and then substitute that into here, and that should allow me to solve for y. So I got 49 minus y squared is equal to 36 minus x squared. So that's going to be minus 25 plus y squared. So this becomes 2y squared is equal to 38, and therefore y squared is equal to 19, and therefore y is root 19. All right, I got y. Now I've got to figure out x. X squared is going to be 25 minus 19. X is therefore the root of 6. Right? Okay, and then now I just got to figure out z, and I'm done. So z, any of these will be sufficient. Let's use that one. Say z squared is equal to 36 minus x squared, which is 6. So z is therefore root 30. All right, great. I've got it all. So we go back to our original formula. X, y, z. We got root 6 times root 19 times root 30 all over 6. And that looks like a big number. But let's break it down into prime factors. You can put it all in the radical sign. 19 is a prime. And that's going to be 3 times 2 times 5, right? Yeah, all over 6. And that's going to be the 2 and the 2's, that you can bring that out. 3 and the 3's, you can bring that out. And then 19 times 5 is 95. 95's got to stay in under the root. So I've got 2 times 3, which is 6 over 6. So this is just root 95. All right, great. Worked out nicely. So this question number 18, the answer is C. In the expansion of 1 plus x squared plus dot 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 until x to the power 27, multiplied by 1 plus x squared all the way until x to the power 14, all squared, what is the coefficient of x to the power of 28? I will begin with a small example, and that is something like this: 1 plus x squared, all squared. Something small that I can easily explain. If I do that, if I expand it, I will just expand it using our standard procedure. And if I do, I get the following: 1 plus x squared plus x squared plus x to the power of 3 plus x to the power 2, x to the power 3 plus x to the power 4. Collecting like terms, I get 1 plus 2x plus 3x squared plus 2x to the power of 3 plus x to the power of 4. Now what I wanted you to notice in the coefficients is 1, 2, 3, 2, 1. You see how it kind of starts off 1, 2, 3 and then goes back down 3, 2, 1? That is what I wanted to illustrate. Because when you do it for this guy, big long guy, it's going to be very similar in terms of the way it behaves. All right? So that's what I wanted to show you. So let's do this big guy right here. Now I'm not going to expand it out entirely. I just want you to see the pattern. So when you expand this, I'll just do a few of them. You get 1, 2x plus 3x squared plus 4x to the power 3 plus dot, 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 right? And eventually in the middle, you will get something like 14 x to the power of 14 plus 15 x to the power of 15 plus 14 x to the power of 16 plus dot, dot, dot. And then at the very end, if you keep going, you'll get 4 x to the power of 25 plus 3 x to the power of 26 plus 2x to the power of 27 plus x to the power of 28. Okay, so I hope you can see that pattern. The coefficients 1, 2, 3, 4, it'll keep going up until 14 and 15, and then it'll go back down 14, 13 down, all the way down to 4, 3, 2, 1. Do you see that there? Very similar to here. It went up 1, 2, 3 and then went back down. In this one, it went up all the way 1, 2, 3 to 14, 15, and then it went back down 14, 13, 12, all the way down 4, 3, 2, 1. Okay, so now we have to do this guy as well. So let's bring that one in. So I am multiplying this guy by this whole thing that I expanded earlier. Okay, now the good news is we only are concerned with the coefficient of x to the power 28. So that's the only thing we care about. So therefore, that's the only thing that I will write out. Okay, so let's do it slowly. 1 times, which one of these gives me a power of x to the 28? Just 1 times that guy, right? So that's the only one I'll write out. 1 times x to the power 28. It's the only thing I'm concerned with is the coefficient for that. So next one, that times this is the only thing that I need to be concerned with. So it will do x times 2x to the power 27. All right? So you get the pattern here. The next one is this times this, because that gives me x to the power of 28, and that's what I need to figure out the coefficient of. So 3x to the power 26. All right? Do one more. It'll be x cubed times 4x to the 25. Right? It just keeps going like this. And then eventually, if you get down to the middle numbers, you'll get x to the power of 12 times 14x to the power of 16 plus x to the power of 13 times 15 times x to the power of 15 plus x to the power of 14 times 14 times x to the power of 14, and so on. And then eventually, to finish it off, at the very end of the train, you will get x to the power of 26 times 3x squared, and the very last one will be x to the power of 27 times 2x. All right? And that is illustrating all the coefficients of x to the power of 28. Now we have to look at them. What are they? Well, that's a 1, right? This is a 2. This is a 3. I'm looking at the coefficient. This is a 4. Then eventually it gets to 14, 15, and then it goes back down again. So the coefficients of x to the power of 28 are of the form 1, then a 2, then a 3, then a 4. Then eventually you get to a 14, a 15, a 14, and then you go back down all the way 3, and then 2. There's no 1. Notice. Okay, so that's a little bit of a trick there. So I've got to add up all these guys. That's my total coefficient for x to the power of 28. Okay, it's not a problem. These first guys are basically the sum from 1 to 15. So that's 15 times 16 divided by 2. And then these last are the sum from 1 to 14, but subtract 1. So that's going to be 14 times 15 all over 2, and then subtract 1, because there's no 1 here at the very end. So this looks like 8 times 15, so that's 4 times 31, 20. And this looks like 7 times 15, which is 105, and then minus 1. So that's 225 minus 1, so 224. And that is the coefficient of x to the power of 28. So number 19, the answer is C. Triangle ABC has AC equal to 3, BC equal to 4, and AB equal to 5. Point D is on AB, and CD bisects the right angle. The inscribed circles of triangle ADC and triangle BCD have radii of RA and RB respectively. What is RA over RB? A little bit of a primer before we begin, and that is something called the angle bisector theorem. And it states the following, that if you have a triangle and the triangle has sides A, B, and then you take a line and cut the angle between A and B in half with an angle bisector, that will divide the hypotenuse, or the other side, not necessarily a hypotenuse, into 2, and that is C and D. And the angle bisector theorem states that A over C is equal to B over D. Okay, so we are going to use that in our question. So let's begin. The first thing, of course, is the angle bisector theorem. This angle, they tell us, is going to be cut in half. But they tell us that AC is 3, BC is 4, and AB is 5. And since that definitely represents a right Pythagorean relationship, we know that this angle is 90 degrees. So when you cut it in half, it becomes 45, like that. Okay, so that's the first part of the question that you have to recognize, that this is a 90-degree angle. So now what I need to do is, using the angle bisector theorem, figure out the length of DB and figure out the length of AD, like that. So if you recall, using that theorem, it would be 4 over DB is equal to 3 over AD, like that. Now, this whole thing is 5. So that means that any of these can be written in terms of 5. So instead of 4 over dB is equal to 3 over AD, I can write 3 over 5 minus dB, like that. Okay? And if you cross multiply, you get 20 minus 4 dB is equal to 3 dB. And therefore 20 is equal to 7 dB, and therefore dB is equal to 20 over 7. And there we go. That's why we have 20 over 7 there. And in a very similar way, you can figure out that AD is equal to 15 over 7. Why? Well, you can use the angle bisector theorem, but a simpler way is that AD is equal to 5 minus BD. And BD, we just figured out, was 20 over 7. So therefore, AD will be equal to 15 over 7. And there we go. We just got AD. Now, the next thing we have to figure out is the length of CD, that bisector. And to do that, we will use the sine laws. The sine law, using that on this triangle, BCD, you get the following. BD over the sine of 45, which is this angle right here, is equal to CD over the sine of theta, where theta represents this angle right there. Now, the good news is that BD, we actually have a numerical value. It's 20 over 7. The sine of 45, we know, is root 2 over 2. That's a standard number that most of you probably have memorized. And then CD is what we're trying to figure out. Now, what about the sine of theta? Well, the sine of theta, since this angle I have denoted as theta, that is opposite over hypotenuse. Well, the opposite is 3, and the hypotenuse is 5. So, sine of theta is 3 over 5. So there we go, 3 over 5. And if you solve for this, you will get CD is equal to 12 root 2 over 7. So those are the 3 calculations that are going to be very important in our question. The value of dB, the value of AD, and the value of CD. Right there. Now, there is a certain aspect of this question that definitely needs to be recognized, and that is that you can do a ratio of the area of the triangles. And which triangles? This one, ADC with BCD. Right? And the reason is because they have the same height. I can draw a perpendicular. Please note that CD is not a perpendicular. I know it's tempting to make it one, but it's not. A perpendicular perhaps is going to be something like this. the location of the perpendicular is not important. I just need to illustrate that those two triangles share the same height. And because they do, we have the following relationship. The area of ADC over the area of BCD can be connected as follows. ADC is what? 1/2 base times height, right? Well, the base of ADC is AD, which is 15 over 7, right? We calculated that. And multiply that by height, where height is this red line that I just drew. BCD, again, 1/2 base times height. The base is BD, which I just figured out was 20 over 7. And the height of that is the same, h. This, as you can see, clearly the h's cancel, and all you get left with is 15 over 20, which is 3 over 4. So the ratio of the area of ADC to BCD is 3 over 4. Now, at this point in the question, there is a very interesting and challenging rule that a lot of people don't know, and that is that if you have an area of a triangle, it can be connected to the radius of the circle that is inside and the perimeter of the triangle. So I'll write it out in words. The area of a triangle is r times s, where r is the radius of the inscribed circle and s is half of the perimeter of the triangle. That's a very interesting rule, and that is what we're going to use to figure out what they want us to figure out in the question, which is the ratio of RA to RB, where RA is this radius and RB is this radius. So we've got ADC over BCD, and that is equal to, right here, RS. So R of A, which is the radius of that circle, times S, which is half the perimeter of ADC. And then that's all over BCD, and using the same formula, it would be the radius of B, which is the radius of that circle right there, times half the perimeter of the triangle BCD. So this is going to give me my RA over my RB, and then I've got to use the perimeters. So the perimeter of ADC is 15 over 7 plus DC, which we figured out earlier was 12 root 2 over 7, and then plus this 3 right here. And we have to divide that by 2 since it's half the perimeter, but because this is a ratio, it doesn't really matter. And same thing, the perimeter of BCD, it will be 20 over 7 plus CD, which is 12 root 2 over 7, plus 4, all over 2. And then ADC over BCD, we just figured out previously was equal to 3 over 4. So this whole thing is equal to 3 over 4. And then if you isolate for just RA over RB, you do all this math, it gives you the following result, 3 over 28 times 10 minus root 2. And therefore that is what they want us to figure out. And for this question, number 20, that would be 3 over 28 times 10 minus root 2 is choice E.